This last topic on atomic size was one that I kind of promised. I want to go ahead and explain why within the same period, as you go from right back to left again, why do the atoms get bigger? And we talked about why it must mean that actually the attractive forces over here are kicking in, and the repulsive forces over here go ahead and make it larger. So we can explain that by something that can be calculated for all electrons around all elements called the effective nuclear charge. And the effective nuclear charge, how do I say this, takes into consideration kind of what's going on in the nucleus and this shielding that's going on with the non-valence electrons. So it kind of looks like this. Oh, wait a minute. I guess instead of showing you the last thing, I want to bring up this little sheet I made to talk about effective nuclear charge. So it's going to kind of, well, you'll see. So effective nuclear charge, we show it with Z, we call it Z star, and it's like a little superscript asterisk. And it describes how much the valence electrons are drawn in towards the nucleus. The outermost electrons are those valence electrons. So we calculate the effective nuclear charge by taking the number of protons in the nucleus, and from that we subtract they're going to actually be the shielding electrons. We subtract the non-valence electrons. They provide this shielding effect. And that gives us kind of what the positiveness kind of feels like, the nucleus sort of feels like. So I have an example. I'm going to take a couple of elements. I'm going to pick on magnesium first. So magnesium has 12 protons in its nucleus, and it has 12 electrons then that are configured as you kind of see, the 1s2, 2s2, 2p6, 3s2. And we talked about actually the valence electrons would be those 2 electrons found in the 3s subshell. So the way we calculate the effective nuclear charge would be the number of protons, 12, minus the number of shielding electrons. So those are non-valence, minus the number of shielding electrons, non-valence electrons. So I get 10. Do you see where that's 10? 2 in the 1s, 2 in the 2p, and 6 in the 2p. So that's 10 electrons. So we have an effective nuclear charge of plus 2. So each one of those 2 valence electrons in the 3s subshell are feeling the pull of a plus 2. Okay? So that's kind of, they're sort of independently feeling that pull. Well, let's go ahead and look down the period, and let's pick on phosphorus. It's in the same period. Phosphorus has 15 electrons, it has 15 protons, and if it's neutral, it has 15 electrons. So we find homes for these 15 electrons, and it looks like this: 1s2, 2s2, 2p6, oh, I missed my 6 there, 3s2, 3p3. Now, in this case, we have, of course, 5 valence electrons in the 3s2, 3p3. Those are our 5 valence electrons. The black ones are our inner or core electrons. So we come up with an effective nuclear charge of the nucleus of the phosphorus atom. We take the 15 protons and we subtract the 10 shielding electrons. Now notice that for magnesium and phosphorus, they have the same number of shielding electrons. So we have an effective nuclear charge of plus 5. So plus 5 kind of is the way I think of those 5 valence electrons in 3s2, 3p3 are actually, the valence electrons are seeing a pull of plus 5, which is a more attractive force than the plus 2 for the magnesium. So for that reason then, those 5 valence electrons are pulled in more tightly to that phosphorus atom than those 2 valence electrons for the magnesium atom. They get to kind of fluff out because they have a smaller effective nuclear charge. So I hope this helps. That's kind of the way that works. So I have a slide here to kind of summarize that, I think. Okay, so what you saw a minute ago between the magnesium atom and the phosphorus atom is that those 10 electrons actually shielded the valence electrons from the positively charged nucleus. So that had the same shielding, okay, but the effective nuclear charge for phosphorus was greater than, because it had more protons in its nucleus. So if that doesn't make sense, that's fine, but that's kind of what goes on behind the scenes for an atom getting smaller as you go from left to right across the same period. So don't forget, these are a couple of problems then to do for this part 6. And again, you will see some questions of some sort about comparing sizes of atoms on your Unit 2 exam.